Hi, I'm Murti Salapaka. I'm from the University of Minnesota Twin Cities. I'd like to take the opportunity to thank the organizers for giving us this chance to talk about our research. Today, I'm going to focus on reconstruction of interconnectedness in networks of dynamical systems based on passive observations. This passive observations is an important qualifier, as we will see, is the focus of this particular talk. Let me come to the motivation for this passive observation-based reconstruction of influence diagrams. Another important area for reconstruction from passive means is stock market data. Here too, you might have time series of various stocks, and then from this time series you need to reconstruct the influence pathways, and the purpose could be you would like to see diversify your portfolio, so you would like to pick and choose stocks from different kinds of sectors which don't have too much influence on each other. Here too, also the same common characteristic is that it is possible that one stock influences some other stock in a time dated manner or in a dynamic manner, and of course loops are possible in this as well. So there's another example of where passive observations based reconstruction is important is that of climate or meteorological data, where you're getting time series data of temperatures at various locations, and you'd like to reconstruct the influence pathways of how a region is affecting another region, how temperatures in an ocean, for example, are affecting temperatures inland. And here too, it's not possible to influence the actual dynamics, and you need to reconstruct using time series passively. Moreover, here the time series might show some kind of periodicity, for example, could be yearly, seasonal periodicity, or daily periodicity. The actual algorithms, I would like to present a data generative model which will tether the construction algorithms or reconstruction algorithms, and will provide some kind of measure of fidelity of how well the algorithms reconstruct the network. The algorithms by themselves can be used without any assumptions of data generative models, but data generative models are there to provide metrics or measures on how well is a reconstruction algorithm. So I'll present one model here. It's not necessarily all-encompassing, but it's the first model, but other models, nonlinear extensions, can be easily done on the model that I'm presenting now. So one data generative model is the following, whereby we assume that data series, time series data xj here is getting influenced by xi through some kind of operation here. For example, if you can assume this operator to be a linear time invariant operator, in which case you can represent this through a convolution operator. And then we also assume that this xj time series has its own innate characteristics being captured by ej here. And so ej is something that is particular or specific to xj. It's not coming through any kind of other processing that is going on. And so here is how the influence of xi on xj is captured. Essentially, xj due to xi is hji, and that influence is also added, its own innate influence is added by ej. So here is a multivariate influence, whereby x1's influence is captured on xj through hj1, and xi is in this setup is captured, influence of xi on xj is captured through hji, and then we have all these influences added up, and then the innateness of xj captured by ej, and therefore you end up with this particular model is xj is ej plus this particular summation of hji z of xi. I'm putting the z here just to indicate here that we're dealing with linear time invariant systems, and this could be thought of as a z transform or a filtered version of xi's. ej we will assume are independent, so ej is independent of ei if j is not equal to I, and if I vectorize this, I'll get this setup here, which is captured here. So if I make this into a vector, I'll see this linear dynamic influence model or data generative model. Xi's are ei's plus this kind of a dependency matrix xi's, and E is the noise, the innateness such the power spectral density is assumed to be positive, and more importantly the independence is captured by its diagonal structure, And in more, we can because we're dealing with passive observations, we can assume these are all steady state processes. So the statistics is wide sense stationary. And in other cases that we saw, for example, in the climate and rotating machines examples, it could be cyclostationary, or there could be polyperiodic signals that might characterize these signals here. Okay, and the main topic, the main discussion here is to first create a graphical representation. So if you have a linear dynamic influence model or a linear dynamic data generative models, we have these xi's and we have these influences coming from x6, for example, through h16. So this h16 is non-zero. Then we have to have we in the graphical representation we place a directed link from 6 to 1. That is, the influence of 6 is coming onto 1. And similarly, if you look at x2 here is e2 plus h29 x9. So x9 has an influence on x2. So there should be an arrow from 9 to 2. So if you look at this, this particular 9 to 2 link is here. And finally h21 x1. So you have this 1 influencing 2 is that signifies this. In this diagram, we don't represent the noise. And this is left implicit in this whole assumption, but you can clearly see that this is the topology directed graph that comes about by taking this particular approach of representing this data generative model through this. Now, I would like to point out that in this case, the only data that is available are these xi's. The structure is not known, is completely unknown. We don't know the statistics of EIs, except for the fact that these EIs are all independent. And from that, we have to address solutions to the following problems. H of z is unknown, so none of the structure is known. X is measured, all xi's could be measured, or a fraction of them are measured, in which case we have latent nodes. There could be data corruption. And under these kind of X characteristics, what is the data measurement characteristics? One has a detection problem where you need to determine if HJI is 0 or not, which is a Boolean problem. And then we have a more complicated problem, more involved problem of estimating the actual influences. So that would be determining HJI of Z. So this is a data generative model that I will emphasize here, even though there are easily nonlinear extensions of these models that is possible. Okay, so now I'm going to talk about some network reconstruction algorithms. I just give a shout out to all my collaborators here, Professor Andrew Lampersky from University of Minnesota, Professor Donatello Matarasi from University of Minnesota, Dr. Deepjyoti Dekha from LANL, Saurabh Talukdar from Google, Harish, Venkat, and Mishfad are students in the lab who have worked on this network reconstruction algorithms. I'll focus primarily in this talk on projection and estimation based algorithms, even though there are other methods that we have pioneered, but I'll not have time to go over those methods here. So first off, let's talk about the non-causal projection method. So there are a bunch of projection methods. I'll touch upon two of them here. In the non-causal projection methods, the idea is straightforward. It is you try to estimate the present time series data on the rest of the past, future, and present of the rest of the time series data. So here I have xj of t. If you consider this as t here, you're trying to estimate xj of t based on the past and the present of the other time series data, the past of other time series data, and the future and the present of the time series data. And so here is the algorithm. You're given these time series data. You project xj on the span of the variables xi of tau, where tau is all the times in the past, present, and the future. And you create this particular estimate, and this estimate depends, the xj's present time t estimate is based on the xi of tau in the past and the future and the present through this weight wji of t comma tau. T is indexed to capture the time at which you're estimating the process xj. And if you have wji of t comma tau non-zero for any particular tau or any particular t, you put a link between j and I, an undirected link between j and I. So that's the algorithm that is there. Now this particular algorithm is essentially the Wiener filtering algorithm. Some of the properties established by Wiener is this wj of t comma tau, which is the weight of xi at time tau on the estimate at time t of xj of t. It just depends on the lag and does not depend on the specific values of t and tau, but only on t minus tau. So wj of t comma tau is wj of t minus tau comma 0, and I'm going to use some abusive notation to just label that as wj of t minus tau. And then the filter here I'll again use further abusive notation to write down wj of z. When I put z, that is simply the z transform of these coefficients wji of k here. And Wiener also showed the particular filter here. This filter here can be recovered from the cross spectral densities of the phi j bar inverse of z, and essentially this j here is essentially the j bar here is essentially a set of all the indices that are not included that remove xj from it. And so you get the cross spectral density here and the spectral density of j bar here, and you get this particular inverse done, and then you get this wj star from there. So you can get the filter, the Wiener filter first, and the Wiener filter can be used to get the coefficients of the impulse response wjik, and this wjik would be this particular coefficients here wj of t minus tau, t comma tau will be wj of t minus tau. So one could go down the route of getting past spectral densities and then finding out the Wiener filter and then coefficients of Wiener filter, or you can use a projection based method here. Both of these algorithms, going through projections or going through cross spectral densities, have their own place in the reconstruction algorithm, and I'll focus on the cross spectral density based method in a different slide as well. This projection method allows for us to different kinds of projection. So here I'm pictorially representing the projection at time t for xj on the strict past of all the rest of the nodes and including the xj itself, and again forming an estimate here. So if you look at here in this projection span, I'm including all the variables that are in the strict past of xj of t, and I have this particular filter here, and I put a link again between j and I if any of the contributions of xi of tau in the strict past include a weight which is non-zero in forming the forming the estimate of xj at time t. So this is another algorithm that we can use for what is the grandeur projection, and we can use this on the data. By the way, none of these two algorithms right now assume any underlying generative model. You're just working with time series and getting these estimates out. Another way that I would like to just emphasize is the inverse cross spectral density. I touched upon this when talking about Wiener filters. One could just take the x vector here, stacked up x vectors time series, and create the cross spectral density, the spectral density of phi xx inverse, and then put a link between I and j if phi xx inverse ij is not equal to 0. So this is another approach. So both this approach and the first approach of non-causal projections, we're putting an undirected link, whereas when we are doing the time arrow based stuff, we're putting a link from I to j if there is a non-zero coefficient wji which is capturing the influence of I on the jth one. So clearly here, that is the three different algorithms that are presented, and let's see how well they perform. By themselves, this can be applied to any time series data, but we like to see how they perform on some assumption of the generative model, and that will be the next part of my talk. Okay, so now some results which will assume a data generative model, and using the data generative model, we would like to, for example, understand what is the fidelity of reconstruction. So before going to that, I'll like to present what do we mean by a Markov blanket. So this is a directed network here, and we are considering this particular node shown in red. These two green here, which are influencing the red dot here, are the parents of this particular node. And if you look at this, these two nodes here are children. These three nodes are the children of this particular node. And if you see this particular node here has a child which is shared by this parent, but there is no direct link between these two. So what you see here is that this one is a common child with no direct link, which means that these are strict spouses. So you can have a spouse relationship when two particular nodes share a child. So we have the set of children, the set of parents, and the set of spouses. Spouses are essentially nodes which have a shared child. In this case, the set of children, parents, and spouses forms a kins, and the Markov blanket is basically essentially of a particular node is the set of all kins in that particular. Our first method of what I'm going to call non-causal construction, which is also Wiener construction, Wiener filter based construction, as I argued before that they are equivalent, even though implementation wise they might be different, but I can essentially use the Wiener projection on the strict past, on the past, present, and the future based projection, and put a link between j and I if wji is not equal to 0. And this wji not equal to 0 essentially is captured by putting a magnitude bound on wji and seeing if that is bigger than tau. Then you put a link between j and I without any directions. So the main result shown in this particular article of ours is that given this true generative graph of linear dynamic influence model that I presented before, given this particular graph, which is of x equal to e plus h of zx, essentially the graph reconstructed using the Wiener projection or the non-causal projection is that you will put a link between the node and every one of its kins, undirected link, of course, between node and every one of its kins. So essentially here you have this particular nodes here, and then you have a spouse here with no direct link between these two. However, when you reconstruct this, you're going to put a link between the spouses as well. So you put a link between this particular node and all of its kin. These are strict spouses, and so those links come into this picture here, but you of course reconstruct the links between the parent and the children as well. So you essentially create the Markov blanket or recover the Markov blanket by this criteria of magnitude on the projection weight. So that's the result that is there in this article here. So reconstruction algorithms, just to demonstrate that this works, here is a data generative model of linear dynamic influences. Each of these arrows shows a transfer function that is non-zero. And if you look at the reconstruction, the Wiener filter based or non-causal projection provides you this particular structure here, where between 3 and 9, which share a common child, there is no direct link, but because they share a common child, they are spouses, so it puts an arrow for between the spouses. So you reconstruct this graph here, which has which is a moral graph because it's putting link between all spouses. So it recovers the moral topology. We can generalize this notion of projection not just for assuming Whiteson stationarity. You can use the same algorithm of projections on polyperiodic data. So here is the actual data here where the transfer functions are there, and then there are different periods present in the past spectral density, and you can use even the same essentially the same kind of ideas on projection on polyperiodic data by lifting techniques, and show that you can recover the moral graph. So here, for example, are not Whiteson stationary, E is not Whiteson stationary, but some cyclostationarity is there, in which case we can recover the moral graph again. Here there is a link between these two because these two parents have a common child here, so they're spouses, and so we reconstruct this graph, this particular reconstructed graph. So these ideas of projection need not be just restricted to Whiteson stationary assumptions, but also some cyclostationary or polyperiodic data assumptions. What happens if you do a strict projection on the strict past, on the projection on the strict past of the Granger filter kind of argument here? In that case, what happens is if you have this particular generative model, you actually recover everything that you have with the directions also. So then one would ask, what is the importance of the non-causal projection? The importance here is this reconstruction happens perfectly only if you further assume that a data generative model includes strictly proper transfer functions. So this transfer function is strictly proper, which basically restricts the application of this when we have direct effect between nodes. So non-causal projection will work if you have direct effects without strictly proper transfer functions, which captures in some sense the delays, that strict delays exist between the influences that we have. And there's a whole class of problems where that kind of assumption can get violated. So here, under the assumption that the data generative model has a strictly causal transfer function, we can recover the graph perfectly with directions, but albeit with that assumption that you have strict causality of the underlying generative model, data model itself. Then, and here is a reconstruction of the graph of this, assuming that all these transfer functions here in the degenerative model are all strictly causal. We're able to reconstruct using the Granger filter based or the projection on the strict past based idea. We can reconstruct the arrows here perfectly. I left out the reconstruction based on the cross spectral density part, and the results are same as that we get for Wiener filtering. Essentially, you can reconstruct the moral graph topology from that from this particular inverse cross spectral density matrix methodology as well. Okay, so this kind of captures when we have full data available, all the nodes are being measured, and there is no corruption of data, there are no latent nodes, nothing. And now I will transition to the case where we start having measurement data corruption. What happens if the data is corrupted? Number one, what kinds of data corruptions can we incorporate, and find the extent of the influence of data corruption, and furthermore start talking about latent nodes in the process. Okay, so now we come to spurious links. We have already seen that the non-causal projection based method or the cross spectral density based method both lead to spurious links between strict spouses that don't exist in the original graph, and there we're using only perfect measured data, and so that already includes the spurious links. However, of course, spurious links can also appear if the data corruption is there. So I'll tackle both of these issues one after another. So let's start with an application here of RC network representation of a building here with different rooms with heat flows Q1, Q2 to Q7, and there's an RC model here which is supposed to underlie the data generative model with thermal resistance being measured, represented by resistors, and the heat capacities being measured or represented by capacitors here. The underlying model here is of course going to be bidirected here because it's a physical network, and most physical networks have this bidirected nature. That is, if node 1 influences node 2, then node 2 also influences node 1. So you see this bidirected graph here. The bidirected graph has this particular topology associated with it, where we have dropped the directions, but each of these undirected links represents a bidirected link in the directed graph. Now, in this particular application, we have used real data nonlinear simulation of the entire building, a very high fidelity simulation engine to collect the data, and then nevertheless applied the same algorithm of non-causal projection as. Now, using the projection-based algorithm, we recover this particular model here. So this particular data used for this reconstruction comes from the nonlinear model, and you can clearly see links between spouses. So here, for example, 1 and 3 are spouses because they share a common child 2, and there's a spurious link placed there. Now, in this bidirected physical graphs, what you will notice is that there is a ubiquity of spurious links, and we have to address and remove the spurious links. For the reconstruction of this moral graph, we of course have used the weight or if the weight of the projection is 0 or not. It is a Wiener filter coefficient if it is 0 or not, and if it is non-zero, we have placed a link. So it's a magnitude-based test on whether the Wiener filter is 0 or not by some thresholding on the weight of the Wiener filter coefficient. So we can also look at the Wiener filter coefficient and look at its phase. For example, we have created the moral graph using the magnitude of the Wiener filter coefficient, but we could also look at the phase of the Wiener filter coefficient. Now the phase is pi. One can show that if it is pi and a constant pi across all frequencies, then the link is spurious. Also, if the link is spurious, then the weight is going to be, this particular phase is going to be pi. So in summary, we can use the Wiener filter magnitude to construct the moral graph, and then which includes links between spouses, and that could be spurious. But then you can use the phase relationship to remove the phase of the Wiener filters to remove those spurious links here. Now, till now we have not included any other corruption, but of data everything is assumed perfect. Now I come to the case where the data is corrupted. We are still measuring all nodes, but the time series data coming from these nodes could be corrupted. I will specifically focus on two different models of corruption, even though the methodology is applicable to a much larger class of corruption. So here I have my original generative model. X is h of z x plus e, but I'm adding my actual data that I have available is this ui of e ui here, which could be a nonlinear function of the original data series, time series data, and some parameter here which captures stochasticity here. For example, both of these data corruption models fall under this class, where supposing you have a packet drop, then your corrupted data stream ui of n is xi of n with probability pi. So you're with probability pi, you're getting the actual data stream, and if it's possible with probability 1 minus pi that you have dropped that packet, in which case you retain your original original value of ui of n minus 1 to become ui of n. So that's one packet drop model. Or you could have temporal uncertainty in the time sense. So if you define tau I of n to be n plus k1 with probability pi and n plus k2 with probability 1 minus pi, then ui of n could be fi of tau I of n, in which case ui of n becomes xi of n plus k1 and ui of n becomes xi of n plus k2 with probabilities pi and 1 minus pi. Clearly here you are receiving the packet, the data packet or a time series packet, k1 delayed with probability p1, k2 delayed with probability 1 minus pi. These both kinds of uncertainties are quite practical, and one would like to know if there is a way to assess the damage of this data corruption. And so here is a result which captures the extent of the data corruption. So let's assume that you've already created the model graph through some means, might be non-causal projection based or Wiener filter projection based or cross-spectral density based. So supposing you have the original graph, you have a model graph of this particular graph, and then once a model graph is there, you can create the perturbed graph conceptually from the model graph. So the perturbed graph is simply created by first characterizing what is the set of nodes that are corrupted, and assuming the rest of the nodes are not corrupted. You find out if between two different nodes I and j, if there is a path which is strictly a subset of corrupted nodes, so all nodes in that path are corrupted, then you include that link in the model graph, and that would create the perturbed graph of the original network. Interestingly, the result we have is to show that if you construct the graph based on projections on the corrupted data u, so you just have that available to you, you take that u data and do, for example, non-causal projection or Wiener filter basing projection or the cross-spectral density based method, then the model graph that is recovered will be equal to the perturbed graph of the original system. So you have an original graph has a model graph, that model graph, you add links to that model graph by adding links between two nodes if in the model graph there is a path which exists which is completely consisting of the corrupted nodes. You get the perturbed graph. So with this particular projection on the corrupted node data u, you will recover the perturbed graph. For example, here if you have this particular structure, and if this is the corrupted node, if you look at this particular structure, there are only children here, there are no spouses. So the model graph will be the same node, same structure here of the original graph. This is the structure. And if only this is corrupted, we know that even if you use the same kind of if you use a corrupted data, only two being corrupted here, you will recover this particular graph, which is a model graph, and there is no corruption pretty much in the recovery. However, if this node is corrupted, and you base now your structure, the model graph for this particular structure is still the same thing here. However, there is, through this particular node, there is an undirected path to all the other nodes. So there is going to be a perturbed link through all the other nodes, and everything gets connected to each other and becomes a clique. So this is what you would recover if this node gets corrupted in the original in the original graph. So that gives you a nice way of characterizing what is the extent of perturbed nodes or corrupted nodes, and what extent it will be. And this kind of an idea of something getting isolated and something getting a clique kind of a network can be used further to triage location of these perturbations and location of these corrupted nodes as well. Okay, so now I'll talk about latent nodes and via an application to the power grid. So the distribution power grid is mostly radial, but now increasingly loops are becoming possible because of various new technologies coming into place and integration of renewables into it. So here, for example, there is a loopy network, and there are buses here. Each of these buses, you have the ability to measure, for example, the voltage signal. The voltage signal can be characterized by the magnitude of the voltage and the phase of the voltage signal. It's usually the 60 hertz sine wave. So the phase and the magnitude provide the measurement at each of these particular bus nodes that you see here. And then the idea is to reconstruct a physical network from this phasor measurements at each of these nodes. Now this is not, each of these nodes is giving you the magnitude of the voltage and the phase of the voltage. These are not time series, these are fixed values of magnitude and phase, not time related, so there's no dynamics in this being considered. But all the methodologies that we have presented for dynamically related data hold here, because we're just looking at random variables now and a direct connection here, a direct relationship here, a static relationship here. However, the same kind of ideas, all the ideas will go through, because this is just an instantiation of the general framework where we are using the time relationship is simply instantaneous time relationship. So here V theta, V is stacked up all the voltages at all the nodes, the voltage magnitudes at all the nodes, and thetas are all the phases of all the nodes with respect to a reference node. So we stack them up, and you can show that this V and theta are random vectors here, which get related from P and Q. P and Q are the active power and reactive power respectively injected at each node, and those P's are stacked up and Q's are stacked up. So these are vectors of power injections, active power injections, vector of reactive power injections, and this is the relationship you get between the voltages and the phases at each node, relation with the active power and reactive power. There's enough evidence in literature to show that in many cases it's reasonable to assume that this active power and relative and the reactive power injections are all stochastic, and also that they are spatially uncorrelated. That means that the active power reactive power pair here is not correlated to the active power reactive power injection at some other node, because they have independent loads. Essentially, at the load usage is different at each of these nodes. Okay, so once we have this relationship between the vector, the measured, the variables voltage and phase theta vectors, and how it relates to this PQ, this becomes a data generative model for V theta. And what we see here is we are in the Gij, which is the inverse of the the line parameter here. If Gij is 0, means that these RAB, XAB are infinite, which means that this link is not there. For example, if GAB corresponding to this is 0, which would mean RAB is infinity and or XAB is infinity, which would imply that this link doesn't exist. So the whole problem becomes understanding when is Gij 0 or not, and it's very same ideas will help in the sense that you take this V theta measured measurement. For example, if this was the connectivity of the physical topology, you take those V theta measurements at each of these nodes and find the inverse covariance matrix, and then find out the ijth element and put a link. Then you would recover the modal graph, and you could do the same thing with projections as well, that you project the time the voltage signal being captured at each one of these nodes and on the rest of them, and then look at the projection based approach, and you're looking at the weights of the projection. You can reconstruct this modal graph, and again you will find the spurious links coming up like before, and you can use the phase criteria, in which case you look at the sigma V inverse, which is the covariance matrix inverse. Ij phase is less than 0, then you remove the link, and you can recover the entire graph. So this is similar story to what I have told before, when all the nodes are being measured. What happens if you're not measuring all nodes? Of course, you can apply the same inverse covariance ijth element not being equal to 0 condition to first recover the magnitude-based model graph within quotes model graph, and then use this technique to remove spurious link the phase one. But you still see that there are a lot of spurious links remaining in this particular graph, and that is because sigma v oo inverse where is not including the effects. Sigma v oo inverse does have effects coming from 11 and 12, and so it could be non-zero without having any direct links even in the model graph. So that includes spuriousness. So that gives us a hint on how to reconstruct this in the following sense. Let's do some analysis of this. If you look at the sigma v, which is the covariance matrix of this v here is a shorthand for v theta, the voltage and the phase of the voltage signal. So if you look at the voltage magnitude and theta stacked up, that is v here. So the sigma v star can be further broken up into the observed part of the covariance, observed and hidden, hidden and observed, hidden and hidden. We cannot compute these three here, but we can compute this. And then look at the inverse of this matrix. Inverse of the matrix will be JVOO, JVOH, JVHO, and JVHH. And if you look at this sigma OO inverse, then gets connected to this through this Schur's complement to give you JVOO, and then this part is all through the hidden nodes that you have the influence on sigma VOO inverse. So if you're able to characterize only this part, this probably has the required information without having the information seeping through into this part of the matrix through this hidden nodes. And of course that happens to be true, but we need to first find out what is the sigma VOO inverse. What is the sigma VOO? And to do that, we have to solve an optimization problem whereby we look at the structure of this particular decomposition. We see that the sigma VOO is sparse, and this part is low rank, because assuming that there are a few number of hidden nodes and many observed nodes, this becomes a low rank matrix, and this becomes a sparse matrix. It's sparse in the sense that there are n square connections, but typically any particular graph has only order n connections, and that's why we are saying sparse. So it becomes a problem of decomposing this into a sparse plus low rank matrix, and you can use one of these kinds of optimization problems to solve for the sparse plus low rank reconstruction part. This is a star norm used here and L1 norm used for sparsity imposition, and that is being imposed for the rank conditions. And and there's a whole bunch of literature on this as to how to do sparse plus low rank reconstruction. I'll not go into that here. And then the result that we have is, once we have this JVOO constructed, we can now use this part, which is not corrupted by the influences of hidden nodes, to use the same kind of conditions, and the relationships, the results that we obtain are pretty interesting. We can use the magnitude constraint on JVOO first, and then just use so we don't have this graph available in the beginning, we just have data available from it. We first find sigma OO, take sigma OO inverse, compute this, solve for JVOO, put a threshold on JVOO, magnitude constraint, magnitude threshold to reconstruct this. This still has spurious links. Then we apply a phase-like condition on this, which is JVOO plus J theta OOIJ less than 0 is exactly the phase condition with a threshold value, and we recover the true links here. So these are the true links here, but we need not recover all the true links. So we have to look at this structure and this structure here again, and we further do some triaging here, and I'll show you a method of triaging here. So we look at here 9218. And in this magnitude, after the magnitude constraint was imposed, we see this kind of links determined, and there is a link between 9 and 1, which is not there in the true link after the phase condition was applied. But you can deduce that link would be present because these are all true links now. Even if there's a true link and there is a common child, remember everything is a bidirected, so 2 is a common child, that would induce a 9-1 in the model graph reconstruction, and that's what you see here. Similarly, a link between 8 and 2 would be there because 9 is a common child, and that's what you see here. So we can explain away the 8-2 and the 9-1 link here, so we don't have to put any hidden node here, so there's no hidden node here. Now in the true links here, we don't see a link between here between 4 and 5. We do see a link being induced between 4 and 5. That would mean that there is a hidden node. That's the only way you can have in the model graph a link coming between 4 and 5. So we put a hidden node there. And between 1, 7 and 3, there is no, in the true link, there is no links between 1, 7 and 3. So what that would mean is, to create this structure, of course, if there was a hidden node, then we would induce this kind of structure in the model graph for reconstruction. So we put a hidden node there, and using this data of hidden nodes being there between one hidden node between 1, 7 and 3, one hidden node between 4 and 5. So we know that 4 and 5 have one hidden node, 7, 3 and 1 has one hidden node. So we have constructed that part of the graph, this part of the graph, and now we know we input all this true link 7, 6, 5. So hidden node 6, 5 and in this manner. 3, 4 is a true link. So we put 3, 4 true link, and then the hidden node connected to 3. So that part of the structure is reconstructed, and this hidden node is connected to 1. So we recover the entire topology using this particular method here. So I've given you a glimpse of how to triage out hidden nodes, and using the sign criteria and the magnitude criteria to in consonance to reconstruct the entire graph. This result works in general if the minimum cycle length is 5 and hidden nodes are separated by at least 2 observed nodes. And you can look at the article associated with this for more details. So we have used this for a real power grid application with nonlinear simulation. So the actual mat power simulation, so data is generated from underlying nonlinear model, but the same algorithm being applied for the nonlinear model that you see in blue, and you can see what happens to the reconstruction fidelity as the number of sample increases. For about 10 to the 5 samples, we start getting almost true construction that we have, and the details are all provided in this particular article. This is loopy network with 33 nodes, hidden nodes separated by at least 3 hops, and this is a modified IEEE 3 bus line. Okay, so let me just conclude by saying that we have provided reconstruction based on passive methods without actively intervening in the network operation. In the case when all nodes are measured, when the nodes are corrupted by some kind of imperfections, data corruption is occurring, and how do you characterize the extent of the reconstruction, the reconstruction, how the errors in the reconstruction can be characterized when in the presence of data corruption. Then provided some glimpses in how to reconstruct the underlying topology from in the presence of latent nodes, and then showed some applications to practical problems. There's a whole bunch of research that I can't get into here, but nevertheless very interesting directions. These are the articles that I would point to if you're further interested. This is topology learning of linear dynamical systems with latent nodes using matrix decomposition. This goes into much more detail into how do you solve this kind of a problem, sparse plus low rank decomposition, taking some work from from Chandrasekharan at Caltech, and then use those kinds of results to further the work, not just for random variable case, but actually for stochastic processes. And then we have the estimation part addressed here. How do you estimate the transfer functions rather than just looking at the detection part of it, and how can you estimate robust to the structural part, how can you estimate transfer functions, and there's very interesting results on structural uncertainty in the system. Then there is a nonlinear extension of the problem, how to recover directed graphs from directions as well in a nonlinear setting using directed information under data corruption. So that is this result here. And then we have furthered these results, as I said, to cyclostationary processes and also applied it to grid topology. So this is what I will point to if you are further interested in our research. Thank you.